Hello, friends. I finally finished making all the reviews for all the units, so I've put them all together here into one place. So it's the mechanics review for the entire course. And so if you see breaks, like it's over and then it's starting again, it's just because I'm taking all six of the videos and putting them into one video, and you can just put it on as fast as you want and review before the test. So good luck. Thanks for watching. Don't forget to like and subscribe. Hello, friends. Today, we're going to start reviewing for the AP Physics C test for mechanics. I'm going to make a series of videos, have them separate, and then put them all together as well into one big video in case you want to watch that. So let's begin. We start with just the really, really basic ideas, all stuff that you probably would have covered in honors physics or, AP Physics 1, something like that. So distance, right? The differences between distance, path length, displacement, right? Remember that displacement is a vector. It has the arrow above it, right? Distance and path length can be different things, right? Average speed. Average means that you're taking that over a period of time. Average velocity, that's the displacement over a period of time. There's a difference in the time there. You're not talking about instantaneous velocity or instantaneous um, acceleration, or pay attention to those types of things. It's talking about average or instantaneous. Um, and so if as long as you have a constant acceleration, as long as you have constant acceleration, you can use what we call the VIFTAD equations: V, initial, final, time, acceleration, distance. So it's these types of equations, right? All of these work and they're valid, and you probably have them memorized. You know them backwards and forwards. You see them in your sleep. These only work when you have constant acceleration. If you don't have constant acceleration, that's when you need to use your calculus. And so here's a summary of the calculus. Velocity is the derivative of the position function, right? If you have a position function with respect to time, you take the derivative of that, that gives you the velocity function. Same thing for acceleration. Acceleration is the first derivative of the velocity function. It's also the second derivative of the position function. You can take integrals as well. The thing about the integral is that it doesn't tell you what the instantaneous velocity is or the instantaneous position, but you can use the integrals to find the change in velocity and the change in position. So keep that in mind. That's just this relationship. And then one of the big ideas in physics is that you want to be able to go back and forth between descriptions and functions and graphs and that kind of thing, right? So back and forth. This is all conceptualized graph-wise in this way, right? So here you have a position function, right? Here's a position graph. The slope of this, in other words, the derivative of this, gives you the velocity function. And the velocity function, right? If you take the slope of this, or take the derivative, you think of it that way from the calculus perspective, that gives you the acceleration function, right? So what's happening here, the slope is increasing, so we have an increasing value. Here we have a constant slope, and so we have a constant value on this. And then taking the area under the graph, it's also finding the integral. That gives you the change in uh, velocity. And then here, the area under this graph gives you the change in the position, which you can find over here. Again, it doesn't give you the instantaneous, right? So if you just find like the area here, that's going to give you the change in position from here to here, but it's not going to tell you exactly where you are on the graph. Okay, some other things. Again, the first unit is all so big picture. The first unit, what are you doing? It's kinematics. All we're doing in unit one is describing motion. We haven't gotten into any causes, any forces, right? Any causes for the change in motion. It's all just about describing motion. So that's one dimensional. But then we can get two dimensional, even three dimensional. In order to do that, what we do is we pay attention to things that are vectors and scalars, etc. So um, keep in mind vectors, right? We represent vectors with arrows. It's really useful. The arrows help because the length of the arrow shows us the magnitude, and the arrow can also show us direction. An example of a vector is velocity. Students always like to imitate, the character from Despicable Me, the vector committing crimes with direction and magnitude. Oh yeah, right. He's right. That's what a vector is. Vectors have direction and magnitude. A scalar has magnitude only. So, for example, something like mass, time, Those are examples of just scalar quantities. When you multiply a vector and a scalar, you can just multiply the scalar in, and it gets distributed to all the different parts of the vector quantity. Um, when you do vector addition, right? So that's adding the arrows together. You can do that graphically, where you put them tip to tail, right? So you can add two vectors kind of like this. Here's one vector, and I'm adding it to this vector. And you can see I've put them tip to tail, so the resultant looks like this. Okay, there's the resultant, etc. And then you can also do this, what you could say, analytically by splitting this into components. So you take the vertical component of this one, the horizontal component of this one, the horizontal component of this one, plus the vertical component of this one. So if you put them all into a table, you can add the verticals, add the horizontals, use all your trigonometry, sine, cosine, tangent, split it up, put it all back together, use a Pythagorean theorem, and find analytically what the resultant is. Also, when you're splitting things up into components like that, you can use unit vector notation. That's the IJK. Don't forget about that. It's extremely useful, very helpful. Um, I is your horizontal, J is your vertical, K is your, into or out of the page. Don't forget right-hand coordinate systems. Um, this is just a handy notation to have. And especially when it comes to things like vector arithmetic. I'll show you another thing about vector arithmetic in a minute, but you pay attention to the vectors, right? And if you have this all in unit vector notation, then it works. And you can have everything in unit vector notation. You just add the i's, add the j's, add the k's. Same thing as what you're doing here when you're adding up the components, right? IJK is just a different way. It's a notation for paying attention to those components. Dot product, right? So when it comes to taking, so when you have two vectors and you want to combine them in some way, right? You can add, subtract, etc. It's like, how do you multiply vectors? The thing about the product, it says product here, and there is multiplication involved, but I want you to be careful when you think about dot product. Think of it more as a way of combining two vectors. I don't want you to automatically jump to multiplication, right? Because there's also a cross product, which is another way of combining two vectors. So a dot product is just it's one way of combining these vectors. It's a certain process that you can go through with these two vectors to get another thing that comes out. The thing that comes out of a dot product is a scalar, and so they call it the scalar product. Again, the way of combining two vectors that gives you a scalar output. Okay, it's a process that you put them through. Two ways of calculating the dot product. A dot B is the magnitude of A times the magnitude of B times cosine theta, and theta is the angle between the two vectors. Also, what you can do is you can find the individual components, right? The horizontal, the vertical, the forward, backward components. You multiply the two components together, and then you just add everything up. And that feels really weird. Students are always like, wait, like what? Because we're always taught we keep the vertical, horizontal, everything separate. And it's fine. You do that when you multiply, but then you just take those products and you just add them all together. If you use both of these, by the way, right, if you can find these components and you know the resultants, then you can put these two together to find theta sometimes. Another application here is projectile motion. Projectile motion, it's really simple and it gets messy because it's two-dimensional. So students are like, oh, what's going on? Right. The whole key is that the horizontal acceleration is 0 and the vertical acceleration is g, acceleration due to gravity. And keep in mind that the time is the same. The time is the thing that doesn't matter if it's vertical or horizontal, and it goes back and forth. So find the time here, the velocity here, this time vertically, horizontally, whatever it might be. Finding relative velocity, this could be two-dimensional, could be three-dimensional. Things like, there's a boat on the water or two boats on the water and they're moving relative to the water. How are they moving relative to each other? That kind of idea, right? Or there's a boat in the river is moving. The vector arithmetic works, okay? But you got to pay attention to the notation here and the negative signs. So for example, let's say we've got boats A and B and they're moving on the water. and I want to find the velocity of A with respect to B. That's what this means. VAB is the velocity of boat A with respect to boat B. So I can find that by finding the velocity of boat A with respect to the water, plus the velocity of the water, that would be C, with respect to boat B. So see how these two things combine? It's VAC plus VCB. It's like the C is in the middle, and so it combines, and the C cancels out, and you just get VAB. It's got to be arranged that way. This has to be the velocity of A with respect to C and the velocity of C with respect to B. That means if you know the velocity of B with respect to the water, that you have to flip it, okay? Because this, V of CB, is equal to negative V of BC. It's equal to the negative of the velocity of the boat with respect to the water. And so if you pay attention to these negative signs, to flipping vectors, and to the notation here and the way that this arithmetic is set up, it works. You should always never just rely 100% on equations, right? This formula, this equation, is an expression of something that we've learned, right? Some idea that we've developed. Always, have a way to be checking these ideas and thinking about it, draw pictures, diagrams. It's really important. Sometimes on an open-ended question, you can get credit just for drawing a diagram, a good diagram, even if it doesn't necessarily ask for it. Uh, and then drawing the diagram should help you anyway. So, I mean, every question, equation, diagram, graph, think back and forth between those representations and use them to help you know that you're doing the right thing and to be checking your answers as you go to get a full concept of the question. Okay, so not too long, pretty quick. That's our review of Unit 1, Kinematics for AP Physics C, and I'll see you for the review of Unit 2. Hello, friends. Today we're going to take a look at reviewing AP Physics C Unit 2, Mechanics. This is usually referred to, the way that we construct it, at least the way that I've put the unit together, is dynamics. So basically, Newton's laws. Um, Primarily, Newton's second law. So let's take a look. First of all, whenever you think of a force, I want you to think of a force as an interaction between two objects. Don't think of it as a push or a pull. It could be too abstract. The other thing that happens is that when people are thinking about forces, they just start adding kind of like random forces that are kind of made up. Whenever there's a force, what that means is that there are two objects, two physical objects that are interacting with each other, right? At least in Newtonian mechanics, this is how we deal with it. It is a vector, so the direction matters, and we represent it like other vectors with an arrow, and that tells us the magnitude and the direction of the force. Right. Now, if it's two objects that are interacting, how do we know the direction? Because they're pushing or pulling out each other. What we do is we talk about the force with respect to, this is the force acting on this object. So we're looking at one object at a time and then looking at the interactions of other objects with that one object, right? So we kind of zero in. Newton's second law, right? It's the kind of the basis, the whole foundation of physics. F net equals ma. Again, F net. So we're adding up all those interactions acting on that one object, and then that is equal to the mass of that object times the acceleration. Newton's first law is really just Newton's first law when it's in equilibrium, right? In other words, when F net equals zero, and that's when A equals zero. Oftentimes it's expressed, right? Objects in motion stay in motion, objects at rest stay at rest. That needs a lot of clarification, right? Because there could be lots of forces acting on an object, and yet it's remaining at rest. The whole idea is if the net force is zero, then the acceleration is zero. The velocity is constant. Anytime you hear a constant velocity, you've got to think equilibrium, net force is zero, etc. Newton's third law is just telling us that the interaction between two objects, it's the same magnitude of force between them, and they're just in opposite directions. If you think of a force as an interaction between two objects, the Newton's third law is kind of implied, right? You can't have one object interacting with the other and the other not interacting back on that other one. The phrase, the expression, equal and opposite, when objects interact, they exert. Or no, sorry. The expression I don't like is that for every equal action, there's an equal and opposite reaction. It makes it sound like there's an action reaction type thing. Instead, it's just one single interaction between the two objects. All right, so kinds of forces, and I get in my the way I've constructed my units, I get into other these some of these in other units, right? But so we have here the gravitational force, right? The universal gravitation between any two objects near the surface of the Earth. F little g, right, is mg. G is 9.8. Most of the time, I personally like to round that to 10 meters per second squared instead of 9.8. On the test, if you're doing calculations, may as well be safe and just do 9.8 on the AP test. That is the friction. Right? So the whole idea is that whenever there are two surfaces, there's some coefficient, there's some property of how locked those surfaces are with each other, right? How easily they're going to be able to slide against each other. And that's what mu represents. And then circular motion. I've got a couple examples here with circular motion. But the whole idea here is that we have a net force, a net centripetal force. So this could be one force. It could be a part of one force. It could also be a bunch of forces put together that add up to some net centripetal force. That's equal to mv squared over r. Acceleration is v squared over r. There's some different types of forces, and there are others that come up throughout the course. But for now, in Unit 2, one term that it's important to know is the equilibrant. The equilibrant is the thing that puts a body into equilibrium. So for example, if there's an object, a random object that has a 5 Newton force on it, the equilibrant would be 5 Newtons in the opposite direction. So in other words, right, it's the force that would make that thing in equilibrium, that would make the net force 0. Okay, force diagrams. This is big, big, big thing. Very important here. So what do? You create a circle, box, or dot. Very simple. It's not a sketch of the object. You're not. It's not an art class. Circle, box, or dot. I personally like boxes because then if you have more than one force, you can draw them like on the same surface. But boxes or dots work. The force. Then you draw the forces as vectors. The tail connects to the thing that you drew, the circle, box, or dot. You can have the tails coming from the center or just touching the object, but they have to touch the object when you draw them. So for example, if this is your object and you draw a force like this is no good. Don't do that. This force has to connect to the box, right? Or go all the way to the center. Some people do that as well, right? Again, personally, I like to just go to the surface because then if there's another force there, I can add it like that. And then all forces are clearly labeled. If you're dealing with two dimensions, then what you first you draw the what we call the raw force diagram. Uh, then you show separately the direction of the acceleration, and then you draw a separate force diagram where all the forces are resolved to parallel and perpendicular to the acceleration. Here's an example. Conical pendulum. So that's like, a ball on the end of a string, but instead of just swinging back and forth, it's swinging in a horizontal circle. Uh, so if this is the situation, right, it's at an angle theta from the vertical, and it's going around like this. So at this point, draw the force diagram when it's on this point. Okay, so first of all, here's the raw force diagram. What are the objects that are interacting with this ball? And again, think in terms of the objects, because it would be too easy to look at this and just be like, oh, well, there's a force this way, applied force that way. No, don't do that, right? So there's the string and there's the earth. That's it, two objects. So here, you're going to have the tension in the string this way, and you've got the earth pulling down this way. What's the direction of the acceleration? Well, it's moving around in a circle here, which means that when it's over here on the right, the acceleration is directly to the left, horizontal. So I draw the acceleration this way. Now I know when I break this up into its components, I'm going to make everything parallel and perpendicular to the acceleration because I need that in order to set up Newton's second laws like I did here, right? So now the way this angle turns out, right, the vertical component here is cosine, or it should be cosine. I wrote it wrong. And because when I draw this angle this way, this is where theta is. So ft cosine theta here. And then this is ft sine theta here. That's the horizontal component. Now, from this, once I fix sine and cosine, uh, so now I just write Newton's second law horizontal and vertical, right? Newton's second law parallel to the acceleration. So that's ft sine theta. And then vertically, there's no vertical acceleration, right? And so here, ft cosine theta, get that right, ft cosine theta minus fg is equal to 0, right? That's what the acceleration is. So it's in vertical equilibrium, and horizontally it's accelerating this way. Again, since it's circular motion, I could substitute v squared over r. It all depends on what my next step is going to be, what I'm going to plug in, what I'm going to solve for, etc. Okay. So, I mean, like one thing you could do if you had to, you could use this equation to solve for ft. If you know the mass of the object, you can find ft. And then if you know what maybe they ask you to find FTs and you get that from this one. Uh, or maybe they want you to find the velocity for it to remain at that particular angle. So you find FT, plug FT in here, etc. You go from there. Lots of different things to do, but this is the whole key, right? The reason the force diagrams are so important is because Newton's second law, which is the key to solving everything else, comes directly out of. It's just like an equation representation of the force diagram. Okay, so now when you're creating the force diagrams and you're writing out Newton's second law, it's important to realize that any objects that are moving together that have the same acceleration can be considered a single object. So for example, the Atwood machine, like this, oftentimes, if you're going to solve for the acceleration, people will draw two separate force diagrams, one for this mass, one for this mass, and you've got the tension, and then you end up having to solve for the tension and like set them equal to each other. It ends up getting a little bit complicated, and you can do it. But in the end, when you substitute everything together, you just end up with this. But check this out. These two masses are connected and they do move with the same acceleration. That means that uh, if, you know, I can choose kind of like this direction as the acceleration, right? So this one moving up, this one moving down. If I choose that as the same, so I can treat them as one system. System thinking is super important, right? So what's my system? If I take both masses as the system, then the tension is internal to that system. Newton's second law only applies to external forces. So what are the external forces here? Well, there are only two, little mg and big mg. So when I write the net force equals ma, m total, write that there. So what are the forces? Well, it's just these two, right? This one is pulling in the direction of the acceleration. This one's pulling opposite the direction of the acceleration. So I write mg minus mg equals, both masses are the system, so m plus m times a. And now it's really simple to solve and get the Atwood machine formula, you could say. You get that. And it all just comes out of forming one equation. You put it to, and then you just solve for what you need. So pay attention to systems, and that, because that will also dictate how you can set up Newton's second law. And sometimes you can manipulate things to make it simpler to solve. Here's an example involving friction. Okay, so imagine we've got a situation where there's a block or something that's on a surface and it's being pulled with a rope, 20 newtons at 30 degrees to the horizontal. Okay, well, if it's on a surface, it's being pulled. Oh yeah, and mu k, the coefficient of kinetic friction is 0.2. So I want to know, what is the net force? Well, there's going to be friction to the left. There's a normal force up, earth force down. But here's the key. Because there's an upward component here to the um, tension force, the normal force is not equal to the earth force. It's going to be less. And so let me zoom in here. So now I have that, right, this force diagram, and I know the acceleration is going to be this way based on the situation, what I've described so far. So now I go over, break this up. Okay. I know that I don't know what the friction force is going to be. I've taken the tension force and resolved it, parallel and perpendicular, like this. And so Ft sine theta, so Ft is 20 and sine of theta, sine of 30 degrees is just 1/2. So this is 10 newtons. And then Ft cosine theta, so 20 times cosine of theta is going to be 17.3 newtons. Right. Always good to know your 30, 60, 90, right? So root 3 over 2 times 20, etc. Um, and so I know the friction force now is going to be less than 17.3 because it's accelerating to the right. But in order to find out what the friction force is, I need to know the normal force. Well, the normal force is going to be the earth force minus Ft sine theta times sine 30, right? Because these two upward forces together have to add up to this one. So Fe, so 30, here again, 3, so I'm multiplying by 10. I'm using G as 10. Minus these 10 newtons from the tension force. And so this ends up being 20 newtons. Okay, so the normal force is 20 newtons. So the friction force is mu K times Fn, which is going to be 0.2 times 20. So that's going to be 4 newtons. Okay, the net force then, it's supposed to be a sigma. So sigma F equals 17.3, right? That's this, minus 4 newtons. So it's 13.3 newtons horizontally. There's no vertical net force. It's in equilibrium that way. Okay, so again, what did I do? Start with this raw force diagram. Acceleration's this way. Break this up, and then I'm just using Newton's laws. So again, vertically it's in equilibrium. The acceleration is 0. So these have to add up with these, right? So you get 0 when you add all these verticals together, and then this plus this equals the net force. Some reminders for circular motion too. I did the example of the what do you call it? The conical pendulum as an example for setting it up, right? And again, the key idea that the centripetal force, we call it centripetal force, but really I tell my students never put centripetal force on a force diagram. Always pay attention to the uh, the raw forces, because even like for example, with the conical pendulum, there is no centripetal force. There's no force on here, certainly on this one, that you could put. Some students will just add centripetal force here, but you can't do that, right? Because the centripetal force is actually just a component of one of the raw forces. Sometimes it'll be more than one force, they add up, or it's a component of this and another thing altogether. The centripetal force is always a net force. Treat it that way, and I wouldn't even put it on the force diagram. But then don't forget, right? The velocity, something moving a circle, 2 pi r over t. Capital T is the period, r is the radius of the circle, or 2 pi r f. F is frequency, and frequency, 1 over the frequency is the period. And don't forget the centripetal acceleration formula, v squared over r. Okay, those are the basics. A couple of examples. Unit 2, dynamics, is basically force diagrams and Newton's second law. That's kind of the whole thing. And then just some different ways that objects interact with one another. Well, friends, today we're going to be continuing to review. Today we're looking at Unit 3. Unit 3, the way that I've put the units together is work, energy, and power all together in one thing. So we begin with work. What is work? So work is, one way of looking at it is it's a change in energy in the system. Okay, the way it's calculated is it's a dot product between the force and the displacement, as we see here. Um, Now, if it's like a constant force, if it's a linear, or whatever the displacement is, it's a dot product. But if we have a changing force, that's where we use calculus. This is AP Physics C. And so the calculus version, the AP Physics C version of this equation is integral F dot dx, where we add up all of the product of the force and displacement over time. In terms of units, work and energy is joules. So pay attention to the units. I'm going to tell you now, I have survived entire parts of my physics education, right? I finished with a BS in physics, and I've survived whole parts of my education just by paying attention to units. So, for example, if you know that a Newton is a kilogram meter per second squared, and you know that a joule is a kilogram meter squared per second squared, then you know you have to multiply a Newton by a meter in order to get a joule. That helps you find this equation because okay, newtons is force, meters is displacement. Oh, so if I take force times displacement, that gives me the right unit. It gives me the unit of joules. So, if you're thinking like, oh, is it force divided by displacement? Is it force times displacement? You can think in terms of the units to get the right units. What do I have to multiply to get the right units? To get joules in this case. And so think about this here. Like, as I said, analyze the units. If you have a force versus displacement graph, this is very simple, right? But the whole point is simply that the area underneath, you're multiplying length by width, right? So force by displacement, and that equals work. Newtons times meters gives you joules. So that's the key. Okay, there are types of energy. The main types of energy that we're talking about in terms of mechanical energy that we're concerned with in this class: kinetic energy, 1/2 mv squared. That's the equation for that. Gravitational potential energy, mgh. We abbreviate it U sub g. That's a valid convention. And h is in relation to some what we call a datum, right? So you set where zero height is, and you can have negative gravitational potential energy as a result of that, right? If you set and it goes below the datum, you can have a negative height. You can have negative gravitational potential energy. So part of solving problems is setting the datum in a place that's going to make sense, make it easier for you to solve the problem. Elastic potential energy, so US I abbreviated here. UE could be electric potential energy. So it could get confusing. S works it's like a spring energy or stretch energy. 1/2 kx squared, where x is how much the spring is compressed or stretched, and k is the spring constant of the spring. Now, this equation works, but only for what we call Hookean springs. I may have misspelled Hookean. It might be Hooke, because hook is Hooke. Either way, springs, according to Hooke, work for this. If it's a non-Hookean spring, right? So this is a Hookean spring has this equation, F equals Kx. There are some springs that have a different force equation, different force function. Um, and in that case, you have a different way of calculating the potential energy. And that's related to some of the other topics here, right? So when you're looking at work done on a spring or work done in spring situations, you got to pay attention. Is it the work done on the spring or the work done by the string? So for example, if we say the work done on a spring, right, we're paying attention to the system here, right? What's the system in this case? If we're going to increase the potential energy of the spring has to be part of the system. If the spring is not in the system, then we can't have any elastic potential energy. The spring is then just an outside force. Right? So pay attention to your system. If I'm looking at the work done on a spring, okay, so what would happen? Let's imagine it this way. If I have some force that's pushing this way, right? Somebody like some hand, somebody's pushing. I don't know, I can draw a little stick figure or something like that. It's a giant spring in a box. Anyway, so the person's pushing that way. So the force is this way. And in that case, the displacement's going to be that way also. So here's the delta x, here's the F. Notice the force and displacement here are in the same direction. And so here, by compressing the spring, right, we're doing positive work. We're adding to the potential energy of the system. However, if we're looking at the force done by the spring or the work done by the spring, in that case, the force is actually in the opposite direction, right? As this thing is being compressed, the the spring is doing negative work, right? And in that case, in terms of the system, we're thinking that the spring is outside of the system. So the person's pushing in that direction to the left. Um, and then when the person stops, the balk doesn't have any energy. It's not moving. Why not? Because the spring did equal work in the opposite direction. So the work that the person did, the spring did the work to take it away. Or the person does positive work and adds to the elastic potential energy of the system, right? So pay attention to directions. Yes, work is a scalar, but it can be negative. It can be negative because we can be losing energy from a system. Uh, work can be taking energy away. So it's not, work is not negative in the sense of having a direction. It's not a vector, but it is. It can be subtracted. So pay attention to that force and displacement, and don't forget how to do dot product. Right? That's important as well, which we reviewed in other videos. So let's talk about springs. And we're talking about springs, combinations of springs. This is where we cover it, at least in my course. When you have parallel springs, think of it this way, right? Just real simple. If you have two springs next to each other, that's going to make this thing stronger. It's going to be harder to pull this down than if it were just attached to one spring. So that means the spring constant total, the effective spring constant here is bigger than either one of these, right? We're adding to the overall spring constant. So when they're in parallel, you just add K1 plus K2. If they're more, K3, etc. If you have springs that are in series, what's going to happen here? You're going to be able to pull this farther than if it was just attached to one spring. So it's almost like you've created a weaker spring than either of these. So the operation for getting something weaker, and there's a whole derivation here, which I cover in the lectures in more detail, but just for the sake of review, this is what I call the flip add flip, right? Very technical terminology here that we're using, right? Flip add flip. So what do? We flip, so 1 over K1 plus 1 over K2. I add them together, and so I get this 1 over K total. And then to find K total, you'd flip this back, right? You'd take the reciprocal again. Okay, so parallel, you add them up, and then in series, you do the flip add flip rule. Power. Okay. Power is the rate at which work is done. Okay. It's the rate of energy. So it's dW dt. Another way of getting power, and this is a equation that sometimes students forget, the instantaneous power can be found as the dot product of the force and the velocity. So F dot V will give you P, will give you power. So therefore, since it's the derivative of work, since it's the dot product of force and velocity, it is a scalar, not a vector. The units are watts. It's a little confusing because we have W for work, we have W for watts, but context should always make it clear which capital W we're talking about. Work, so what is work, or what is watts? See, I mix it up. Watts are joules per second. Okay, so if we take joules and divide by seconds, we get kilograms, meters squared per seconds. Whoops, I messed that up. Meters squared per seconds cubed. Sorry. Oh, I went black. Meters squared per second cubed. So take a look at these units, right? The force velocity. Force is newtons, which is kilograms meter per second squared, times velocity, meters per second. That gives you kilogram meter squared per second cubed. So that's the unit analysis for the force velocity power equation. Now, putting all together, conservation of energy. This is the GAPC equation. So my predecessor, Kathy Burns, longtime AP reader who passed all of her materials on to me, she called this the general all-purpose solves everything equation. Pretty good. She toyed with the idea that if she wrote an autobiography, it would be titled GAPC. It's a really powerful equation because you could take any situation, take the initial state. So again, be clear about your system, right? Like if a spring is in the system, you can have elastic potential energy. If it's not in the system, you can't. I had one student one time who he would always make the system just the object. If the system is only the object, that means that there's no potential energy of any kind. All you have are outside forces and work being done. So springs would be work done. Earth would be work done. When you're solving questions, um, specify what the system is so it's clear. Then that'll dictate what goes into this equation. So here's the idea. Some initial state, it's like a snapshot. At that moment, you've got initial kinetic energy and any initial potential energies, elastic, gravitational, etc. Okay, so you take that and you add any work that's done from an outside force. Okay, that will equal the total energy at the final state right? So two snapshots, the initial, the final. It's like 2 moments in time. And then any work that's done, any forces in between could take as long as possible. It doesn't matter. We're just looking at the initial and the final state, the final kinetic energy, the final potential energies, and any internal work that may have been done, or any internal energy. So for example, like there's friction or something like that. And so what's happened there, the system is heated up. So we call that internal energy. You drop an egg and it breaks. That breaking is considered to be internal energy. Um, if there's a runner, like a sprinter who's running or something like that, he's using up internal energy. And so there's a loss of internal energy there. Okay. But this equation can be used to analyze any before and after situation. Um, Oftentimes, later in the course and even in the E&M course, there'll be a question involving like forces and movement or something like that. And it's really confusing, and students try to figure it out. They use kinematics and dynamics, and they forget that they can use conservation of energy. This is what we call time symmetry. Symmetry is where there's been a transformation of some kind, but things remain the same. Conservation of energy is an example of time symmetry. But the total energy at one time is equal to the total energy at another time, even though there's been some transformation that has taken place. We can keep track of the energy and where it goes. Okay. Related to that, potential energy curves, kind of a big thing. It'd be a little bit confusing. It's based on this idea that the change in potential energy is equal to the negative work done by that force. One thing to keep in mind is that any potential energy is due to some kind of force, right? So there's gravitational potential energy because there is a gravitational force. There is elastic potential energy because there is a spring force or some other kind. When you get to electricity and magnetism, there is electrical potential energy because there is such a thing as the electric force. So if we include, say, for example, Earth in the system, then we have a change in the potential energy. That's equal to the negative work done by the Earth. All right. So then if we look at the work done by the Earth on the object, uh, then the change in potential energy is equal to the negative work done. So for example, if you're raising a box, right, as the box goes up, the Earth is doing negative work. Earth is pulling down, it's going up, but the gravitational potential energy is increasing. All right. So Earth does negative work, gravitational potential energy increases. So that's just a demonstration of this. Also, how do we calculate work? Work is integral F dot dx dot product. So we put these two together, and then we end up with this, that the change in potential energy is equal to the negative integral F dot dx. That also means then that force is equal to the negative derivative of the potential energy graph, right? Or the potential energy function. If you had a potential energy function, it would look like this, right? So in other words, if you have a potential energy graph, the negative slope would give you the force. Here's an example. So here's a potential energy graph. Looks like this, right? And so uh, this is zero, right? The slope here is zero. And then it's a negative slope, right? So that means I'm going to take positive because it's the negative of the slope. So if I have negative slope, it's going to be positive value. And this is where it's steepest. So that's where it has the highest value. And then it gets flatter. So the value of the slope is getting closer to zero. And zero here. Okay, now it has a positive slope. Positive slope, positive increasing slope means that I'm going to have negative force, right? Again, the force is the negative derivative. Going that way, I reach some maximum steepness, and then again, zero, right? It's getting flatter back to zero, and so that's what I have here. And then again, uh, getting steeper and then flatter, steeper and then flatter. So that's a higher slope value, and then down to zero. And then following the same pattern, at this point, the slope is zero, and so I have a value of the force is zero, right? If there's no change in the potential energy, that means that there's no force from that from that kind of force. There are a few things to point out here. One, equilibrium. Equilibrium is when the net force is zero, right? So that means that when the force is zero here, that would be here and here. Those are these points. And so that's the places where the slope is zero. You've got a maximum or a minimum. So the way you can find this is take the derivative, set it equal to zero. That's an analytic way of finding this. This we call unstable equilibrium. This we call stable. Unstable equilibrium. Just imagine having a marble, right? So if we put a marble right here, if it goes a little bit to the left, it's going to continue going that way. If I put a marble here and it moves a little bit to the right, it's going to continue going that way. It's unstable. It's not going to stay here if it's moved a little bit to the left or the right. Stable equilibrium, right? If I put this here, a little bit to the left, it's going to come back to the right. If I go a little bit to the right, it's going to come back to the left. So stable, it kind of wants to stay in there. It's a well. And you can think of the potential energy graph as just a roller coaster. Think of it this way. At this point right here, if I had a marble here, or a roller coaster car, something like that, then what horizontal direction is the force? Well, it's in the positive direction, right? And so look, the force in this whole region here is in the positive direction. And the magnitude of the acceleration, where would the acceleration be the most? Well, at the steepest part. Well, at the steepest part, that's where you have the greatest magnitude of force, right? When you're in this region here, what is the horizontal direction of the force on the roller coaster, right? So gravity's pulling down, but the horizontal direction would be to the left, right? It would kind of be slowing down. And so to the left, that's the negative direction. And so the force here has a negative value. There are a bunch of different ways to think about this. Of course, always go back to the equation. The equations are, in the end, the perfect expression of the concepts, right? That's what really helped science to take off was the mathematization of these concepts and Newton inventing calculus, et cetera, right? And then working from there. Uh, but there are these tools that you can use. One of them, definitely the units. So for example, you've got the potential energy graph, U and X, and you're thinking to yourself, oh, what did I have to do? Do I multiply the U and the X or divide? Well, joules divided by meters gives you newtons. So it must be that the derivative, right? Because derivative is dividing du dx, right? Integral is multiplying f dot dx. It's a multiplication that you're doing there. Even though dot product doesn't strictly mean multiplication, it's still how the quantities end up being combined. So use the units. Um, you can think of the potential energy graph as a roller coaster, conservation of energy, etc. Right. So a lot of tools, and it's just synthesizing all this stuff together, and ultimately you can use the equations to justify and ultimately come to the right conclusions. Hello, friends. Today we're going to be reviewing Unit 4 of AP Physics C Mechanics. This is my Unit 4, as it was given to me by my predecessor, longtime AP Physics teacher, reader, etc. And so what we've done is we've saved drag force that really should go in Unit 2 with dynamics. But the thing is we need integrals. We need that type of calculus to be able to do this. And so it happens later in the year, and we include it with Unit 4. So this is drag, and then it's also center of mass and conservation of momentum. So let's begin with the drag. So first of all, in some turbulent systems, the drag equation looks like this: D equals 1/2 C rho A V squared. I call this the Crave equation because it kind of looks like it spells crave. So C is the drag coefficient. This depends on the medium, the surface of the object that's falling or moving or whatever it might be. Rho is the density of the environment, the air, the liquid, the water, whatever it is. A is the cross-sectional area of the object as it's moving through. And then V, of course, is the velocity. That's in some turbulent systems, high velocity, but most often what you're going to see is this type of thing, okay, where the resistive force is negative BV, where B is some constant and V is the velocity. So it's negative because the force is in the opposite direction. The resistive force is in the opposite direction that the velocity is. If you have a falling object, then the terminal velocity, in that case, mg, right, the resistive force is equal to negative bv. The resistive force and the gravitational force equal each other. If we set them equal to each other, then v equals mg over b. This is how you find the terminal velocity of an object, where this is, again, it's where the resistive force is governed by this type of function. Now, notice if we want an equation or a function for velocity as a function of time, we don't have that. Right? We have velocity in here, but we don't have time. And so here is the um, derivation for finding that. It's a derivation that does sometimes show up on the AP test. I know I put it on my tests. So this is what it looks like. We start with this. So if an object is falling, always a good idea to start with a force diagram, which I did not do here. Shame on me. Um, so if we have a falling object, then we know that there is the uh, earth force down and the resistive force up. So then in that case, we get mg minus r, g minus r equals ma. That's just Newton's second law. Okay, now we know that r is negative bv, so mg minus bv equals ma. ma is equal to dv dt. That's how we define what acceleration is. Fine. So now what we're going to do is we're going to separate the dv and the dt. We get them on separate sides of the equation because what we're going to want to do is integrate. We don't want dt. We're going to want something that's just in terms of t. And so we get dt over here and we separate everything, right? dt ends up on this side and then dv ends up on this side, but I want v with the dv. So whatever, wherever the v is, I've got to somehow get it. So I'm manipulating the rest of the stuff just to get v with dv on that side because when I integrate, I'm integrating with respect to v. So whatever v is has to be on this side with dv. Now, uh, so that's just a repeat, I think, of what I had before. 1 over m dt. Yeah, okay. So now when I want to integrate this, integrate this with respect to v, I can't do this right away. I have to use u substitution. And so I set u equal to this thing, mg minus bv. That means du is negative b, right? Du dv. If I take du dv, I take the derivative of this with respect to v, mg disappears, and then negative b, so negative b. And so I get that dv is negative du over b. I don't know why that negative ended up there. Need to get rid of that. Okay, so dv is negative du over b. I need that because that's what I'm going to substitute. dv turns into this, right? This thing gets substituted in for dv. And then here on the bottom, this is 1 over u. Now I can integrate. And I'm skipping over to this side, moving around a bit. So negative b over m dt. So what I do is I take the negative b here and I multiply it to the other side. So I got negative b over m dt equals 1 over u du. Nice and simple on this side. Now integrate. The limits here is just from 0 to t. On this side, though, the limits, the initial value of u, the velocity initially is 0, right? This is an object that's dropped from rest. So the initial limit is mg, and then mg minus bv, where v is just the velocity at this later time, t. When I integrate this, this ends up becoming negative b over mt, and then natural log, right? The integral of 1 over x is natural log of x. And then I plug in, so this would be natural log of mg minus bv minus natural log of mg, but using logarithmic identities and properties, we can simplify it to this. Negative b over mt, so on that side. Now, in order to get to, I'm trying to solve for v now at this point. I'm just solving for v. In order to get v out of here, I exponentiate both sides. So e to the negative b over mt equals mg minus bv over mg. Again, I'm still just trying to solve for v, and now I'm going to follow this going up to here. Right, so I multiply mg to both sides, just do a little bit of algebra, right? So then I subtract mg over to this side, negative, divide by b, factor out mg, and we end up with mg over b times 1 minus e to the negative b over mt. So let's think about this for a second. At time 0, uh, this equals 1, right? Because this is, yeah, so e to the 0 power is 1. So 1 minus 1, this is 0. So v initial, right, v at time 0 is 0. What does the function for this look like? Well, after a long time, after t, if t is very, very large, e to the negative, very large number, it's like 1 over e to the infinity, then this is just 1 mg over b. And so it's asymptotically approaching mg over b. By the way, that's what we came up with for terminal velocity earlier. Starts at 0, goes there. Key things on the tests, right? You want to note what these values are. This one is 0. It's coming from 0. You can label it as 0. But then we also want to label if there's an asymptote or other important value, initial value, we want to make sure that we label that. If you want an acceleration function, just take the derivative of this, with respect to t. So that's a summary of drag, right? And I went through that derivation because it does show up. It's a good derivation, practice derivation to kind of go through. Let's see. All right, so now momentum. We're thinking about momentum. P equals mv, very simple. Now, interesting to note, F net equals ma. What is ma? Ma is dv dt. And so m times dv would be dp dt. So F net is equal to ma, but it's also equal to dp dt. This is actually how Newton um, defined his second law. We do it differently because of pedagogy, the way we introduce ideas in the classroom, high school curriculum, etc. But when Newton defined this, he said the net force is directly proportional to the rate of change of the momentum of the object. Right? Conservation of momentum. Here's the whole idea. If the net external force is zero, then momentum is constant. If you think about it, that's just Newton's first law. Right? If the outside force is zero, then the velocity is constant. If the velocity is constant, the momentum is constant. Okay, and that's true for a single object. It's also true for a whole set of objects, which we'll see. J is impulse. Um, Personally, I don't like the term impulse. I wish it was just change in momentum. We could just call it change in momentum. Impulse makes the people think about force. So, impulse, impact, that kind of idea. So when you hear impulse, just think change in momentum. Just replace it in your mind. Algebraically, it's force times delta t. And then here, F, it's integral F of t dt. And so let's take a look at the units for this real quick. If we've got newtons times seconds, that is a kilogram meter per second squared times seconds. And the seconds cancel out, you get kilograms meters per second. And that is the set of units for momentum. So it works, right? Pay attention to the units. They work. When you have elastic collisions, an elastic collision is where the kinetic energy is constant. It's the same before and after. Sometimes you'll have a complicated thing where like they don't give you one of the final velocities. This is a handy little equation that showed up in a derivation that I did in the lecture. And if you're trying to find velocities, if you can pack this one away in your mind, it might come in handy in a complicated calculation. Okay, inelastic collision, all it means is that kinetic energy is not constant. If it's perfectly inelastic, it means they're sticking together. However, in all collisions, momentum is constant. Anytime you have a collision in a problem, you want to be thinking about that in terms of momentum. If it's elastic, great, you can use energy. But for that kind of an interaction, that kind of an event, you want to think before and after the momentum is constant, as long as there are no net external forces, right? But then even if there are net external forces, you can take that into account with the impulse, force and time, etc. You have a series of collisions, so something like some mass, a series of particles hitting something to be calculated this way. V average is negative n over delta t, right? So n is the number of particles, and then the total change in momentum. Okay, and so the change in momentum is m delta v. That means that so m times the number of particles is going to be the total change in mass. Right? And so the mass, this is like the mass rate, the rate at which mass is hitting the object, and then that times delta v. This is going to give you F average. Notice how the units work out, right? Meters per second divided by seconds, meters per second squared times kilograms. So it all works out. Two-dimensional collisions, just a reminder that when there's a glancing blow, as they call it, right, two-dimensional, usually it's 90 degrees, unless they say something otherwise, right? The angles from each other, the angle of the resulting velocity vectors, the angle between the resulting velocity vectors, 90 degrees. If you have changing mass distribution, right, this is rocket science. Sometimes people will say like, hey, it's not rocket science. Well, this time it is. And so you got a couple of equations, relationships you're going to use. So T is thrust, R is negative dm dt, right? And that shows up here. It's the fuel consumption rate. So the idea here is that, it's like a stream of particles, except that the rocket itself is losing mass as time goes on. And so that's what R is here. It's the rate at which the rocket is losing mass. That times VREL, the relative velocity. So we get this equation as well. It means the same thing. That equals ma, right? And ma equals m times dv dt. dv dt is the rate at which the velocity is changing. That's the acceleration. M is the total mass. Also, this equation comes in handy. A lot of this stuff is kind of like plug and chug usually, but we want to understand the concepts as well. The change in velocity of the rocket is going to be equal to the relative velocity times the natural log of the initial over the final mass. Okay. So your rocket science equations. Real rocket science gets more complex than that, but it's the basic intro. Okay, so center of mass, algebraic center of mass. Again, in the way we structured our course, we cover algebraic center of mass right away in Unit 1, so we do something hands-on, create something. And the whole idea is that if I want to find the location of a center of mass, that's going to be in just meters. It's just a location. But mass has to be involved, right? So I have 1 over the total mass times uh, each individual mass times its location, right? You just kind of add all those up. What happens is the kilograms cancel out and you're just left with meters on the locations. The calculus version of this is that the sigma gets stretched out into a big S, and then you're adding up the location times the little piece of mass, the infinitesimal piece of mass that you're adding up. So 1 over m, that stays the same. Integral x dot dm, or x times dm. It's not a dot product because neither of these is a vector. Okay, so then um, different mass densities. You can have linear mass density. So this is the Greek letter lambda. That's m over L, also dm over dx. If you have a derivation that involves calculus, you may need to end up with the calculus version of this. So it's how much mass there is per length. So this would be like a rope or something like that. Actually, you could take anything and analyze it just in turn according to how much mass there is given any particular width, length, etc. Sigma is surface mass density, so it's two-dimensional. So it's how much mass there is per every section of area, or dMdA. And then rho is what we normally think of as density. It's how much mass there is per volume. And then the calculus version would be dmdV. Okay, so here's a derivation example. Imagine that there's a rod of length L, and the linear mass distribution is given by the function lambda equals alpha x, right? Lambda is linear mass density. And so alpha is some constant and x is just the location, right? So how would you know what the linear mass density is here? Well, alpha, whatever alpha is, times whatever its x coordinate is. Okay, so we start off with our function, with our basic formula. Center mass equals 1 over m integral x dm. What is dm? So I go back, I'm looking at this, and this is going to be, lambda is dm dm dx, right? And so then dm, this thing, I can substitute in lambda dx. I have to do that because I'm going to integrate x, but I can't integrate x with respect to m. So I need to get this in terms of x. I need to get it in terms of dx. All right, and so lambda also is alpha x. So it's a substitution game where finally now I have all the x's involved. I have to substitute in alpha x here because lambda is in terms of x. I'm doing this in terms of x, so I've got to make sure I've got all the x's in there down to the bare bones. I'm going to factor out the alpha and simplify, so I've got alpha over m integral capital L, so from 0 to L. I'm adding up all the mass, this whole area. I'm going to find the center of mass, right, with respect to that whole thing. X squared. So I take the integral, I get alpha over m x cubed over 3 from 0 to L. And then when I plug in 0, I get 0. Plug in L, and I get alpha over m L cubed over 3. Now, usually we're not going to want this in terms of m. We want to know the location. If I have m in there, then I don't really know the location yet, right? I can't put my finger on what the coordinate is. So now I need to find out what m is. But with m, to find the total mass, I just have to add up all the little infinitesimal pieces of mass. And I can do that using calculus, right? So dm is like the substitution I used before, lambda dx, 0 to L. And then from 0 to L, alpha x dx, that's what lambda is, alpha x. Take the integral, I get alpha x squared over 2 from 0 to L. So this is the total mass in terms of L, which is fine. As long as I know the length, then I can plug that in. This gets plugged in this equation. I plug this into here, and I end up with this. Simplify, you get 2/3 L. So at a place 2/3 of the whole length, that's where the center of mass of this object is. Just a sample derivation kind of practice. If you have a system of particles, Newton's second law holds the the mass, the um, m times the center of mass is equal to just the sum of m. It's like the equation we had before. We just multiply the 1 over m, the m to the other side. Also, the momentum, m times v center of mass. So you can find the momentum of the center of mass of a whole mass of particles, whatever they are. It could be like a solar system or something. And then, so you just take um, the sum of all the momenta, and then the mass times acceleration. So the net force is, again, you just find the mass times acceleration of all of the individual particles, add them together. And so what you end up with is that ma equals F net. And again, that's just Newton's second law. And then if F net is constant, right, or F net is zero, then the velocity of the center of mass is constant. And that's just Newton's first law. So you can have all kinds of interactions, whole systems of particles. But as long as you can keep track of the center of mass and analyze that, then you can analyze what are the outside forces, etc. There you go. That's our unit 4, drag, momentum, and center of mass. Okay, today we get to rotation. Rotation is like the big thing, and it's tough, right? Because what it does is it pulls together everything you've learned, except now it's spinning, and it's in Greek. So let's jump in. Um, So, kind of one of the basic things here. Actually, this isn't even so much a rotation thing, but just turning. So we've seen this before. Centripetal acceleration, right? So that's v squared over r. With our new notation, that's r times omega squared. Omega is angular velocity. The units are radians per second. So got to know radians really well. Here's another form of the equation too. If we plug in 2 pi r over t, the velocity, that would give you the tangential velocity. So you can simplify it. A lot of different ways you can manipulate this. One of the things that's going to happen is that you have problems where you have to manipulate and go back and forth between some of these forms, substitute, change, solve, etc. So as the thing is accelerating, it has centripetal acceleration. If it's in rotation, right, it has centripetal acceleration, and then it may also have tangential acceleration. In other words, the velocity, the tangential velocity might be changing. In that case, the total acceleration, right, linear acceleration, is a tan plus ac. These are linear accelerations, by the way. So that's a kind of basic thing to get out of the way. Now, here's the Greek and the different quantities in rotation. So instead of displacement, or instead of position, we have angle measurement, theta. Standard unit for this is radians. Always check your calculator. Are you in radians or degrees? Instead of velocity, you have v, you have omega, which is angular velocity. This is how it's related. V is r omega, s is the arc length, r theta, r is the radius, distance from the center of rotation. A becomes alpha, and tangential acceleration is r alpha. Okay. Instead of mass, we have moment of inertia. And the moment of inertia is mr squared for a point mass, where it's m, and then r is just the distance from the center of rotation. But in general, the general formula is integral r squared dm. So r is the location of the piece of mass, and dm is that infinitesimal little piece of the mass, and you're adding up all of that. The whole idea is that if you're farther from the center of rotation, there's more resistance to angular acceleration. And so that's what moment of inertia is. It's you can think of it as resistance to angular acceleration, just like mass is inertia. That's resistance to linear acceleration. Force becomes tau, F becomes tau, torque, right? So and tau equals R cross F. That's RF sine theta. And the direction, the order matters here because we're going to use a right-hand rule to solve for that. And then uh, momentum becomes L, that's angular momentum. So L, these are vectors, right? And the cross is the cross product. We'll get to this later. And so L, the way you calculate L is R cross P, R cross the linear momentum. Omega is defined as d theta dt, d theta that's over here, delta theta delta t, algebra based, but we know calculus, and so it's d theta dt. Alpha is delta omega delta t, so it's the rate of change of the angular velocity. It's d omega dt, or the second derivative of the angular displacement function or angular position function. Then the other relationships that we have, just like you can find delta V, I'm taking the integral of a dt. So the change in angular velocity is integral alpha dt, and the change in angular position is integral omega dt. Right-hand rule. Okay, first right-hand rule. Clockwise is negative, and counterclockwise is positive. It's a little bit counterintuitive because we think about clocks and digital clocks. Maybe we don't think about this so much anymore, but clockwise for me, it's like this way is negative. Counterclockwise, if you've been through AP pre-calculus, you know that like the way you measure angles going counterclockwise, starting in the first quadrant, second quadrant, that's the positive direction for measuring angles. Also, the direction can be noted according to the right-hand rule. We have a symbol that if something's going into the page, right, we need to do 3D here, and it's a little bit challenging. So into the page is shown this way. It looks like the back of an arrow, right? You'd see the feathers if you were looking at the back of an arrow, and I guess there would be 4 feathers on this particular arrow. And then if it's out of the page, so if you have a vector, trying to describe a vector that's coming out at you from the page, you put a circle with a dot. And again, we can note the direction according to the right-hand rule. So if you want to indicate that something is counterclockwise, like this, what you do is you curl your fingers in the direction. So if I'm curling my fingers in the direction, then my thumb would be pointing out of the page. And so this and this mean the same thing, counterclockwise, and then also this. Kinetic energy. Just like we have 1/2 mv squared for linear translational kinetic energy. So K is 1/2 I omega squared. M and V just get replaced with their rotational correspondence. And that's it for that column. Okay, again, quick here, just going over this stuff. All right, so back to this idea about moment of inertia. It's mr squared for a point mass, or you're adding up all the little pieces. Sometimes you'll have problems where there are different things that you're adding together. There are like these sticks, and then there are these spheres, or these point masses. You're adding them all up, or you've got a function of some kind. So integral r squared dm. Here are the different shapes, the common shapes, right? If you have a ring or a hoop, or you have a hollow cylinder, it's I equals mr squared. For a solid cylinder or for a disk, I should have included that, it would be 1/2 mr squared. Both the same disk or solid cylinder. A solid cylinder is just like a disk that's been stretched out, right? Same thing for the ring and the hollow cylinder. Solid sphere, I is 2/5 mr squared. Hollow sphere, 2/3 mr squared. The way you can think about this, both spheres start with a 2 in the top, and it's either 2/5 or 2/3. If you have a solid sphere, more of the mass is near the center. And if you have more mass near the center, then you're going to have a smaller moment of inertia. It's not going to resist angular acceleration as well as if everything is spread out farther from the center. And so a solid sphere is going to have a smaller coefficient on the moment of inertia than on a hollow sphere. Thin rod about the center, 1/12 ml squared. It's the smallest one we have. Thin rod about the end, 1/3 ml squared. And that brings us to the plane figure theorem and the parallel axis theorem. So the plane figure theorem only works for a figure that's a plane figure, right? So like a sheet, or it could be a ring or a thin disk or something like that. And the idea is that if it's in the plane or if it's in the plane xy, then the moment of inertia through x and the moment of inertia through y, if you add those together, that'll give you the moment of inertia around the third axis. Okay. The parallel axis theorem, that would be like what we use here, trying to go from this to this. This axis is parallel to this one. So I would take this moment of inertia. So you take the moment of inertia through the center, and then you add the mass times your distance from the center squared. And if you do that, you can try that, right? Because what is this? This is 1/2 L. So if you take 1/12 ml squared plus 1/2, or m times 1/2 L squared, right? When you add that together, you get this. There's a derivation for that in the lecture that I did. Useful theorems. All right, torque. R cross F, RF sine theta. This is the vector product. The units are Newton meters, by the way. Pay attention to the units here, where things cancel out, things come in. You got radians, and then where the radians cancel out and become meters, because you got like meter per radian, all different considerations. But for at least torque, it's Newton meters. And the way we find the direction is through the right-hand rule, or if you know how to do the cross product using a matrix, then you can do that. Again, the order matters. The idea is you stick your fingers in the direction of R, You bend your fingers in the direction of F, and the thumb gives you F, gives you the direction of the torque. There are other ways of doing, like this, different kinds of things. That's the one that I find most useful. That's what I use. I teach that to my students, and then they learn other ways as well. When it comes to product, uh, dot product and cross product, right? Scalar product or vector product. We tend to think product and we think multiplication, but instead I want you to think about product as a way of combining vectors. Okay, so it's not just, oh, this is how you multiply this kind of thing. It's not multiplication. It's a different kind of operation. So it's an operation that's done on two vectors to give you a new result, either a vector or a scalar, right? And there are other types of products that you could come up with as well. But these are the two that we use. So just to think about it that way, a vector product, just way of combining two vectors that gives us another vector. Rotational equilibrium. This is Newton's first law. The whole idea is that the net torque would be zero, and therefore the angular acceleration would be zero. It's very simple. Equilibrium problems. So you get situations where something is in static equilibrium, right, or total equilibrium. That means translational equilibrium and rotational equilibrium. So here's what you do. First step, draw a really good force/torque diagram. Draw the object, whatever it is, draw all the forces on there, label X and Y, break it all up. Then you have to choose an axis of rotation for torque. You have to choose and you can choose any axis of rotation, it doesn't matter. So it's always good to choose an axis of rotation where you get something to cancel out, right? Because the distance R is zero. And then you write out your equations. The net horizontal forces add to zero. The net vertical forces add to zero. If it's three-dimensional, the net third dimension forces add to zero, and the net torques equals zero. So you have those equations, and then you start solving. System of equations, get things to cancel out. That's basically it. But everything rests on this. Good force torque diagrams. Do not go stingy on this. It'll cost you later on. This is force diagrams, torque diagrams. That's where you want to spend some of your time to really understand the problems that you're trying to solve. Newton's second law looks like this. Instead of F equals ma, it's tau equals I alpha. I can put arrows on these because technically these are vectors. That's just Newton's second law. And so let's take a look at this. When we have rolling, something that's rolling. So in that case, it's kind of a new thing. Everything else has just been rotating. Here, it's actually moving along a surface. The point of contact, the velocity is zero. Translational velocity of the point of contact is zero. Velocity of the center of mass is just the velocity of the center of mass. The velocity of the outer edge is 2 times the velocity of the center of mass. If you're looking for kinetic energy, total kinetic energy is the rotational kinetic energy plus the translational kinetic energy. When you add them together, what you end up with, if you substitute in expressions for m and I and omega and v, etc., what you would eventually get is this, where it's 1/2 Ig omega, right? 1/2 I omega, except that Ig is the point of contact with the ground. That's your axis of rotation. This has to do with going around the center of mass. When you add the translational kinetic energy, then you end up with 1/2 I sub g omega squared, right? So around this axis. Rolling is only possible if there's friction, so keep that in mind. The idea is that the friction puts a torque on the object and makes it spin. So if something is like sliding up an incline because there's no friction, then there's not going to be any angular acceleration. There's not going to be any torque on the object. And whatever angular velocity it had, it's going to keep. But if it is rolling, so for example, a thing rolling down an incline, the final velocity would be this, according to this expression, right? So 2gh. So you get that looks familiar, right? The velocity of something that falls a certain distance ends up being the square root of 2gh. But notice what's down here. Instead of just over 1, it's I sub cm over mr squared. Okay. Now, moment of inertia is, some coefficient mr squared. So what you divide by mr squared and you get that coefficient. So if it's like a disk rolling down, then this is 1/2. So that comes out to. And so the final velocity, it's like it's going to be kind of resisted more, right? It's not just falling or sliding down a frictionless plane. It's the energy is having to go into rotating it as well. So the velocity of the center of mass is going to be less than what it would be otherwise, according to whatever the coefficient is for the moment of inertia. The angular acceleration, not the linear acceleration of the center of mass also is given by g sine beta. Beta is the angle here, right? The angle of the incline divided by I sub cm mr squared plus 1, right? So with that, if it's not rolling, then it would just be this. But in this case, you've got the coefficient of the moment of inertia plus 1. Okay, angular momentum. Another right-hand rule, another cross product. L equals R cross P. Again, cross product, just think of it as a way of combining two vectors. A lot of substitutions here, right? Because P is M times V. So it could be M times R cross V. You can take a scalar, sorry, a vector product, a cross product, and you can multiply it by a scalar. And that's okay. All you do is you take whatever the result is that you get and multiply in the scalar quantity. Also MRV. Here we're talking about the magnitudes RP. The theta, by the way, that's the angle between R and P. They might not be moving 90 degrees. The thing might not be moving 90 degrees from the um, point of rotation. What you do is you call this the line of action, right? So you start at the center of rotation, whatever that is, and you go out to where the object is. That's your R. Another way, so the rotation way of calculating angular momentum is I omega, right? And so um, the way Newton's second law in momentum form, right? So that was F equals dp dt. Well, tau equals dl dt. And that's also equal to R cross F, right? R cross F is tau. So a lot of different relationships. And again, it always ends up being a lot of like kind of substitution. Don't treat this just like math. It's tempting to get that to that point, but always strive for understanding of the question, whatever it might be. And then conservation of angular momentum. Without an outside torque, the net angular momentum is going to remain constant. This is basically Newton's, still kind of like Newton's second or first law, except expressed in terms of momentum, right? If the net torque is 0, then the angular velocity is constant. Well, if the angular velocity is constant, the angular acceleration or the angular momentum is constant as well. And you see this sort of thing with the figure skaters. I made a YouTube video, a short, holding weights, spinning, and then pulling the arms in, getting faster, because I'm decreasing the moment of inertia. And so omega goes up, the angular velocity goes up, put it out, increase the moment of inertia, angular velocity decreases. Okay, so an expression of this idea of conservation of angular momentum. Okay, and that's it. That's all of Unit 5, rotation. It's amazing. Okay, so, well, friends, today we're going over the last unit. Again, in the way that we structure units in the course that I teach. Unit 6 includes simple harmonic motion and gravity. So we'll start with simple harmonic motion. The very basic uh, information, omega equals 2 pi over t, where capital T is the period, omega is the angular frequency, not necessarily angular velocity, but it can mean angular frequency, right? Like how many angles there are per second that go by. Frequency, don't forget, is 1 over the period. Omega then is also equal to 2 pi f, 2 pi times the frequency. The basic equation here is a cosine omega t plus phi. So omega, angular frequency, if you multiply that by time, that gives you a particular angle. And then, a times cosine of that will give you a certain amplitude, kind of where you are. And it creates a wave, a function. Phi, that's the phase angle, right? So that's shifting it left or right. Remember, if you have a transformation in the function, that transforms it horizontally. If you have a transformation outside the function, like the a, that transforms it vertically. So here, by having a, that's the amplitude that's stretching it. And we never see a midline shift here. We never take the whole thing in, or rarely, I would say. For the velocity, so again, the velocity equation, what happens oftentimes in students in AP Physics 1, they learn these and they memorize 3 different equations, and they have to memorize like, oh, the velocity is this, the acceleration is that. Here, you memorize one equation, this, and then the velocity equation is just the derivative, the time derivative of this, right? So if you do dx dt, this is what you get. And then you take the derivative again, and you get the acceleration equation. And so notice we're back to the same thing, except that it's, negative omega squared times the same equation that you had. Maximum velocity would be a omega. So it would be the absolute value of this coefficient in the front. The maximum acceleration would be omega squared times a. I didn't write that down, but maybe I should. So a max is a omega squared. And what we're really concerned with there, if we're looking at the max velocity or the max acceleration, is the magnitude of them, right? Notice I didn't put arrows above them. In terms of the graph, this is what it looks like, right? So the cosine graph starts at the amplitude, and then it uh, goes to a goes to zero, minimum, zero, amplitude again, right? Or you got positive and negative amplitude, you could say. The derivative of that, right? So the velocity graph looks like this. You can see how they're related to each other. And the acceleration graph is just the velocity graph flipped. Those squiggles shouldn't be there. It's just bad handwriting, drawing this quickly. Okay, other equations. If we take other things we know, now we're just like pulling things together. This is often what we do in physics. We introduce some new concept, and then it's like, hey, everyone else, you're invited to the party. And we just apply everything else we know. So using the kinetic energy, if it's 1/2 mv squared, well, we have a function for v, don't we? So it's 1/2 k a squared, and then this whole thing. So it's just the square of the whole velocity function. So there's a function for what the kinetic energy is. For the potential energy, uh, depending on what it is, like, so this would be for a spring, right? 1/2 kx squared, a Hookean spring. Then we take the position function and we square that. So we get E total then would be 1/2 Ka squared. So in other words, if you take this is the amplitude. This would also represent then the total amount of energy if you have a spring oscillating back and forth. Also for a spring, another kind of handy equation for the velocity is plus or minus omega square root of a squared minus x squared. And there's a derivation for that, and it's in uh, the original video, the lectures, right? So all of my lectures, the whole course is available on my channel, so you can go back and watch every lecture from mechanics if you so desired. You could do that. And in a spring, also omega equals the square root of k over m, right? So, and don't forget omega is 2 pi f. So if we solve for f, then we get 1 over square root of k over m. What I often do, I don't know why, but for some reason in my head, I can't keep straight. Like, oh, is it k over m or m over k? Just think about the units, okay? In K, you've got, it's basically kilograms per second squared. It's a weird thing. But if you were to simplify all the things that are in K, it's kilograms per second squared. And so if you've got kilograms per second squared, frequency is 1 over seconds. A hertz is 1 per second. So then you think, well, how do I have to arrange K and M in order to get 1 per second, right? So the kilograms cancel out with the meter, the mass on the bottom. I have 1 over second squared. Square root of that is just 1 over seconds, and that's frequency, right? So you don't have to necessarily memorize which one's K over M, but then you just have to go through the work. It's real quick. Use the units. Use the units to check your work to help you solve questions. Again, I've survived whole parts of my physics education just by paying attention to units and thinking about what the quantities were and what I wanted them to be. Okay, continuing then, pendulums. That's the other big thing with simple harmonic motion. You've got pendulums and you've got springs. A lot of the pendulum equations depend on what's called the small angle theorem. And I have seen it in some of the grading guidelines that you're supposed to cite the small angle theorem. And that's the idea that at small angles, sine of theta is about theta, right? So less than 15 degrees. So when you're giving an answer, you can say something like, assuming the small angle theorem, blah, blah, just to mention it would be enough. So anytime you see a pendulum question, not a bad idea to mention the small angle theorem. In this case then, right, so if you've got a pendulum swinging back and forth, S is sort of the arc that it cuts out, and X is the linear distance from one point to the next. For small angles, X is about S. It means the tangential velocity, dx over dt, is about ds dt. And then same thing for tangential acceleration, dA over dt is, the second derivative of the this arc velocity, or the arc position, I should say, function, if you have that. Omega root g over L. Again, to remember the units here, I think like omega, well, what is that, right? It's radians per second. So what do you have to do with g and L? G is the acceleration due to gravity, right? Meters per second squared. What do you have to do with this to get 1 over seconds on the bottom, right? Your seconds on the bottom. This also has equivalent forms. F equals 1 over 2 pi root g over L, or T equals 2 pi L over g. This is the leg equation. Pi looks like it has legs, right? It looks like 2 legs. And LG like leg, right? So the legs there. So T equals 2 pi over square root L over g. That is, if you need something to help you remember that. A physical pendulum, that's when you have a solid body that's swinging back and forth. So something like a meter stick, or if you took like a wheel and you hung it up and the whole wheel was swinging back and forth. Regular pendulums like these things, that's really a point mass at the end of an ideal string. For a physical pendulum, there are a couple of equations, and it involves the moment of inertia. I call this the damage equation because you got dmg over I. So omega equals the square root of dmg over I. T equals 2 pi square root of I over dmg. The I that you're looking at here has to do with the moment of inertia about the axis of rotation. So you got to do some math to figure that out. Go back to the other unit to to work with that one. Damped oscillation. So as things are oscillating back and forth, a spring or a pendulum, eventually everything slows down, and so that looks like this, right? Over time, it decreases. So the amplitude is decreasing according to negative bt over 2m, but the omega is also decreasing, and omega prime, or no, sorry, it's not decreasing. Omega, it's a different omega because you've got like forces involved there. And this is omega prime. It's not the first derivative. This is what it looks like. It's the root of k over m minus b squared over 4m squared. You're probably not going to have this memorized for the AP test, but it's good to know that this is a different expression here that goes in there for that. Energy then, the total energy decreases according to e to the negative bt over m. You get used to seeing this. You see this a lot. This form of an equation, even in E and M, we get this kind of thing showing up. All right, so for gravitation now, moving on to the next chapter, this might be another unit, or I think actually in the new curriculum, the way they split up, College Board split it up, this is mixed into some other units. Basic equation, gravitational force Gm1 m2 over r squared. And G is 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. I think they give this to you, but not bad just to know offhand. If we're going to find the force, the gravitational force, from like a large extended body, then what we have to do is to find the force from each individual piece of it and then add them up, right? So we have to add up all the little individual forces. And so that would be Gm over r squared. So this is actually the gravitational field times each little piece of the mass that we're adding up. And so you could do a derivation for a gravitational field that way. And again, in the lectures, I go through a derivation or two, and you can see that. Field, okay, electric field. Think of not electric field. I was just talking about that. Gravitational field. It is a ratio, right? So you go to the grocery store and you buy meat, and it's like $4 a pound. But when you go out, you're not paying $4. You're paying $4 times however many pounds of the meat that you're getting. Same thing here. Field is how much force there would be for every 1 unit of charge. It is a ratio. Fields are ratios. It's the force per unit mass, and this is the way that we calculate it. Little g equals gm over r squared. It also happens to be equivalent to the acceleration in this case, right? Because if you take the force and divide by the mass, then you get acceleration, and that's also what we get here. It works with gravity. Electric field is not the same as acceleration because there you're finding force per coulomb, force per charge, not force per mass. Okay, inside a solid sphere though, so there are some different geometries here. If you're inside a solid sphere, the equation for the electric field looks like this. It's Gm over big R cubed. Big R is the fixed radius. This is not a variable. This is the radius of whatever object it is you're talking about, times R. R is the variable as you go farther out. So this is basically linear, right? It's a linear function because as R changes, it's just R to the first power. Potential energy, so gravitational potential energy, UG equals negative Gm1m2 over R. Looks the same as force equation, except it's negative and R is not squared. This is measured in joules, just like everything else. Here's an example of the potential energy of a system of three objects, where it would be negative G. Just you're finding all the relationships of the potential energy and you're just adding them up. It's not a vector. You can just add everything. Escape velocity. Okay, if you were to fire something off from the surface of a planet, at what velocity would it have to be to reach all the way to get to infinity, right? To get so that it reaches zero kinetic energy at infinity, or when the potential energy is zero. Again, I go through the derivation for this in the original lectures, but the escape velocity is radical 2 gamer. That's gm over r, so I call that the gamer. We see that other places as well, but square root of 2 gm over r. Kepler's laws. First law, planets move in ellipses. Second law, planets sweep out equal areas in equal time. What that means is they're traveling faster when they're close, slower when they're farther away. The key idea here, in terms of the cause of that, is, or you could think of it this way, as conservation of momentum. If you're looking at a problem and there's a satellite and it's close at one point, slow at another point, how do you find, if you know the velocity and the radius of one, how do you find the velocity at the other? You're thinking conservation of momentum for that. Okay, and then Kepler's third law, that the square of the period is proportional to the cube of the semi-major axis. It was a mouthful, but basically it means, right, so t squared is proportional to a cubed. A is the semi-major axis. Like, the concept here is simply that when you've got different objects going around the same source object, like different planets around the sun, the ratio of t squared over a cubed is the same for all of those planets. The closer a planet is, the shorter its period of orbit. The farther away it is, the longer its period of orbit. The orbital speed of a single satellite is v equals radical gamer, square root of gm over r. And finding eccentricity, this is a pretty rare thing to show up, but not a bad thing to know anyway. Eccentricity is 1 minus rp. So rp is the perihelion, divided by a. And I have a here, but I'm thinking actually that this should be ra, now that I'm looking at it, because if it was just rp over a, then that would mean, so when you have a circle, the eccentricity is 0, right? And so that would mean that rp is equal to ra. The perihelion and the aphelion are the same, right? Or, oh no, sorry, RP over the semi-major axis. So A is the semi-major axis is half of this whole thing. So when RP is equal to A, right? When RP is equal to the semi-major axis. So if it's a circle, this is right in the middle. And so this is half of that whole distance. Then this is equal to 1. 1 minus 1 is 0. Have an eccentricity of a circle then is 0. You can think lower eccentricity, more circular, higher eccentricity with a limit of 1, right, then the more stretched out it is. The kinetic energy of an orbiting object is gmm over 2r. And so here's a function or a graph of the energy of an orbiting object. The kinetic energy and the total energy and the gravitational potential energy. So the magnitude of the kinetic energy is half the gravitational potential energy. So when you add those together, then you get half the magnitude of the gravitational potential energy, but on the negative side, right? So E total is 1/2 UG, and K, the magnitude of K, is 1/2 of UG also. That's what that graph looks like. Those are the major concepts to review from the last unit of AP Physics C Mechanics. Check out the other content on my channel. If there are any particular things you want to review, the whole course is there. So don't forget to like and subscribe. Good luck on the test.